Hello, people. Today we continue talking about chapter 9 of Anderson book, and we need to discuss Prandtl-Meyer expansion waves, theory of Prandtl-Meyer expansion waves, second part of chapter 9. Last time we had discussed shock waves, interaction of different shock waves. Please let me know if you have some questions I can answer. You can write in the chat or ask by voice. I will try to track comments in our chat. And meanwhile, I think I can start talking about Prandtl-Meyer waves. Prandtl-Meyer expansion waves, they are another type of flow we may find in many cases. Expansion waves are always supported by acceleration or deceleration of flow. And in cases where you can find oblique shock waves or bow shock waves, you in most of cases can also find such a flow as expansion wave. Prandtl-Meyer expansion wave. Such flow is different with respect to supersonic shock waves because it's, let's say, an opposite process. Is acceleration of flow, where supersonic Mach number or supersonic flow enters in contact with the body and then accelerates due to change of geometry. Just a moment. Let me cancel this sound. Just a moment. Okay, I'm back. Supersonic flow must enter in contact with the geometry that is expanding area of the flow, and exit of this flow is also supersonic. When we compare this flow with shock waves, we see that flow is accelerating, and another big difference is that this flow is continuous and isentropic, where shock waves are not isentropic. So along process of expansion, we have constant stagnation pressure of the flow. Okay, so P0 is constant, which simplifies a lot our calculations. Since flow is accelerating, we also can observe change in thermodynamic properties, drop of pressure, temperature, and density when Mach number increases. Prandtl-Meyer expansion is characterized by several geometrical parameters. First of all, it's angle of body inclination with respect to original flow direction. So this theta we might see is the angle between body direction and vector of velocity before expansion started. Okay, so this theta. And another geometrical property can be seen as mu1 is the Mach angle. We already saw definition of Mach angle that mu is in generally defined as arc sine of 1 divided by m. And dependently on which point this formula can be applied to any point. So Mach angle is important in calculation of expansion waves because it tells us, this value tells us at which position changes in the flow start to happen. Before this Mach angle, flow is uniform and parallel. All flow velocities are equal everywhere. And after mu1, flow starts to curve. This curvature is continuous process, okay? It curves, okay, also according to Prandtl-Meyer flow rotation, we can always find analyzing flow equations, and this you will see very soon. And then second Mach angle is mu2, which characterizes end of process of acceleration and flow rotation. After we have mu2, which is also defined as Mach angle, but already we use m2 as a reference. So mu2 would be equal to arc sine of 1 divided by m2. Okay, 1 divided by m2. And after this rearward Mach line, flow also is uniform. As you remember, flow always follows in supersonic regime direction of the wall, so we always know which would be direction of this flow after changes or after expansion happens. It's also our theta angle. Changes happen only between forward Mach line and rearward Mach line, between these two lines. And this change is continuous. This change has constant entropy, so it's entropic flow. So it means that it can be considered as reversible flow. And if flow goes in other direction, okay, it's possible to calculate backwards. And pressure stays constant. Also, we consider that in such type of flow, we have no boundary layer. Let's say we assume that boundary layer is so small that it does not influence on flow structure. And because of this, we also assume that temperature 0 is constant. So constant stagnation temperature, constant stagnation pressure, simplifying a lot, final solution. So why Prandtl-Meyer? We needed to see from point of view of the model. Model of Prandtl-Meyer flow is built based on geometrical relations on flow velocities. Here on figure 27, we can see undisturbed velocity v, which will start to change due to change of flow direction. Then in this picture 27, we see that flow direction changes. It's denoted by d theta. Okay, infinitely small change of flow direction causes small change of velocity v plus dv. Now this velocity v by dv is acceleration, changed velocity, and also changed the direction, changed direction of the flow. Here we can see a triangle, actually two triangles, right? One triangle is denoted as A, C, and this Mach wave, we can call it, for example, point O, ACO triangle, in which there is one side defined by Mach wave or Mach angle, mu. Okay, this mu we always know, just reminding you, right? There is a formula on the top, just same formula as I just wrote you previously. So we know what is this angle mu. In this triangle, we will know this line on the center until between point A and B. Okay, it's also equal to V. And what we know else? So we know that there is a change of direction d theta. We know that there is change of velocity v plus dv. And since we define already dimension in this triangle, and we define angles in this triangle, and one angle is 90 degrees in or at point O, we have 90 degrees angle. So all other properties could be calculated. What is interesting to us as a result is to find the relation between angle d theta and change of velocity dv. To make it possible, we also find all other angles in this triangle. For example, this near corner C is P divided by 2 minus mu minus d theta according to geometrical relations, right? We know that sum of all angles in our triangle is 180, right? 180 degrees or P. And it tells us all other angles, for example, this one, and the near point B, there are also two angles which we might be interested in. Once we know all these geometrical relations in our triangle according to theorems of geometry, right, and we know vectors values v plus dv, we can find the relation between d theta and dv. Just a moment. I need to attend. Okay, I'm back. Since we can find the relation between these quantities, we may find here formulas written on this screen that Mach angle can be found also in a different form, like tangent of mu. And due to geometrical relations in this triangle, on figure 27, we can find relation between d theta angle and velocity dv and v. Right, then we substitute, then we put together these two formulas, and we find relation of d theta as a function of Mach number, function of velocity differential, and velocity value. After we found this geometrical relation, I think it's quite clear that it's just a purely geometrical solution. We did not involve any type of equations here, of flow equations. We can see that on the left and on the right side we have differentials, and such an equation can be solved by integrating left and right side of this equation. Okay. Left side of equation tells us how angle of body would changes, right? When we integrate, we can change body into some finite angle. And right side of this equation will tell us how velocity will change due to the change of this angle. Luckily, due to works of Prandtl and Meyer, we have analytical solution of such equation. We have analytical solution of this equation. After a few transformations, which Anderson also involves, such transformation that makes transition from velocity to Mach number, and since we must also have some definition of gas properties, also gamma appears inside such formula. And the other method they use is transformation of function due to I think it's Taylor series, right? Taking into account just first part of Taylor series. Anyhow, analytically, function of d theta can be solved, and this solution, this analytical solution, we find in equation 42. And okay, 43. 42 is some piece of this equation. Integrating left side, we receive theta. Says us that rotation of body would be a function when we integrate this part here. We integrate from Mach 1 to Mach 2. Okay, and then this inside equation 43, we can see the difference between Mach 2 and Mach 1. So we take integral function on the upper limit minus integral function on the lower limit. This integral function nu, which you can see here in the middle of screen, is called Prandtl-Meyer function. Prandtl-Meyer function is an analytical solution of this equation of differentials, which you can see on the top of the screen. Prandtl-Meyer function, when we analyze, we can see it's purely analytical, involving trigonometric function of tangent, because definition of Mach angle involves tangent. And it requires to calculate just a adiabatic constant gamma, and also requires Mach number as a parameter. There are no other parameters inside such function. Gamma is constant. I would like to remind you that for air, gamma is equal 1.4, corresponding to physical properties of air. And Mach number we usually know or we can calculate. In such a way, we see a simple way to calculate change of Mach number in isentropic flow. And we can find a relation between change of direction of flow inside expansion wave and change of Mach number. I would like to present you also a small algorithm that Anderson gives as an example to calculate any isentropic flow with expansion waves from Prandtl-Meyer. For example, we have flow, and inside such a flow, we know already Mach initial, M1, and we know geometry, okay, which is described by this theta angle. This geometry must expand, so area increases when flow goes in direction. Then when we have M1, we calculate function of Prandtl-Meyer according to equation 42. This is 0.1 on the next slide. Or same function of Prandtl-Meyer can be seen from Appendix C. It's very simple. Just a moment, I will show you our book and Appendix C, so we can see. It's a relation between gamma and Mach number. Very, very simple. Probably the simplest appendix we may find in Anderson book. So this is, please let me know if you can see, if it's visible.
Not yet.
Okay, let me try again. No, did it appear?
Yes.
Okay, this is Appendix C, which gives a relation between Mach number, Prandtl-Meyer function, and Mach angle, mu, which could be calculated analytically, as we know by formula. Nu also calculated analytically as function of Mach, but because we have this table, we do not need to calculate here in class or for our fast calculations. Just one limitation is that this Appendix C is built only for air, gamma 1.4. If you need to calculate Prandtl-Meyer flow for gas, which is different from air, having different value of gamma, you can use formula 942 and do this process easily. So Appendix C is very simple to use. You can have all, for example, Mach number. For example, I have my Mach number and I can see my Prandtl-Meyer function corresponding this line, and I can see my Mach angle mu, or vice versa. If I already know my Prandtl-Meyer function, for example, I know my Prandtl-Meyer function is 20.73, then I can see that corresponding Mach number is 1.8 and corresponding Mach angle is 33.75 degrees. It's quite important to state that Prandtl-Meyer function and Mach angle in Appendix C are given in degrees. So when you calculate, please pay attention that also when you use function from the book, you can receive in degrees or radians, depending in which program you are calculating. So pay attention on this probably, or maybe you will need to transform from radian to degrees or from degrees to radian, depend on what you are calculating, right? I think if you use by default in MATLAB, you will receive in radians. You will not receive in degrees. So pay attention on this question when you solve some particular tasks about Prandtl-Meyer flow. Just a moment, I will share again notes. Okay, supposed to appear already. So Appendix C is very simple. Function 942, 943, especially 942 is more complex, but it's same as Appendix C. But function 42 can be used for any gas with any other value of gamma. I would like to remind you that gamma may change in some good range of values, right? Smallest possible is 1, but for gamma 1, Prandtl-Meyer flow doesn't exist. If you will try to use gamma equal 1, you will not obtain any solution here, right? Because first part of this equation will give you infinite angle of Prandtl-Meyer function. And usually we can have gamma for hot gas, for gas inside the rocket combustion chamber, for example, 1.1, 1.15, 1.2. For colder gas, like air, already 1.4 values. Could be bigger. Adiabatic constant is depending on the molecular structure of gas you are working with. If it's a mixture of gases, so adiabatic constant is calculated by some weighted average, molecular weighted average. And if it's just one gas, okay, we can use 1.4. If it's air, can be used 1.4. I'm also reminding you that adiabatic constant is not just a ratio between specific heat, but also can be seen from point of view of molecular kinetic energy, is representing number of degrees of freedom of molecule. If we have so many definitions of adiabatic constant, we can use a different approach to determine it. So there is not just one way to determine gamma. But it's another story of another lecture, probably, and then we can return to our Prandtl-Meyer flow. So once we have M1 flow which enters and the geometry is still constant, then we use appendix C or we use equation 942 and we obtain a new Prandtl-Meyer function. Second step, we can calculate Prandtl-Meyer function at point 2, nu of M2. Just simply, okay, if I rewrite this equation, I can find that nu of M2 would be equal to, I will put on the right side, on the left side, on the other side, Prandtl-Meyer function plus nu of M1. I think it's correct, yeah. So in such a way, just very simple, we summate angle of body inclination and Prandtl-Meyer function before changes start to happen. And then from here, we know which Mach number corresponds to, we calculate Prandtl-Meyer function, and we find by solution of equation 942 or by appendix C, which value corresponds to this Prandtl-Meyer function. When we know Mach 2, we can use isentropic relation. Since our flow is isentropic, I can see that, stagnation pressure and stagnation temperature are constant. So we can use the isentropic relations given in the previous chapters to calculate temperature and pressure. Here, equation 44 is giving to us temperature ratio. Temperature ratio is calculated by ratio of functions from, I think, from equation 840, right? From chapter 8, the ratio between static temperature and stagnation temperature. Here, T02 and T01 are same, so can be found this temperature ratio. We already know Mach number at station 1 and Mach number at station 2. Same thing, but using equation 842, we make to calculate pressure ratio. Here we consider that P0 is constant on station 1 and station 2, and we just need the Mach number before expansion started and after expansion finished, using in this formula. These formulas are absolutely the same as we would use in appendix A. Okay. This, for example, this numerator is a number which can be found in appendix A when we see M1, appendix A is a function of Mach number 1 divided by a value which can be found in also appendix A when we are using as a reference Mach number 2. Or we use formula 944, or we use appendix and ratio between parameters in appendix we use to calculate temperature ratio. Same for pressure ratio. I think for us better to use appendix in class, but for your own calculation in MATLAB it's better to use formulas. So this is it, how it's calculated. I suggest that we could make one calculation of such flow. You will see that it's absolutely simple. Probably I even would write on top of this of this algorithm. Just a moment, I will try to remove my notes from here and I can write on the side. And I also would like to show you calculation of geometrical part of this expansion rate. I mean, mu1 and mu2. Okay, where flow starts to change, this one is mu1, and where flow finishes to change is described by mu2. For this, I will use appendix from book. Okay. Let's give some initial values. For example, I will use Mach 1.5 as M1, and for angle, probably it would be nice to have 10 degrees. 10 degrees, okay. So 10 degrees of body angle and 1.5 for velocity before changes start to happen. What is my first step? I see here I have Mach 1, so I will look on Appendix C on the book. I will find my Mach 1.5, and I will note that my angles, I will make rounding, okay? My new one, according to Appendix C of M1, would be equal to 12 degrees. Okay, and my mu1 would be equal to 42 degrees. 42 degrees. I will not use in my further calculation mu1, but this is important information to draw flow structure. So I already know which geometry is which geometry I have inside which my flow changes happen. It can be important when we design structure and we need to know exactly where flow starts to happen and when flow finishes to happen. So in such a region, I can provide some special conditions, for example, special shape or materials that would sustain such flow transformation. So this is why I need mu1. Then after I did this in a very simple way, from Appendix C, second point, I do calculate nu of M2. I know that I have 10 degrees and 12 degrees, so my nu of M2 would be 10 plus 12, and it's 22 degrees. Okay, that's simple. And then in step 3, I will see my Mach 2. Mach 2 is a function of nu of Mach 2. Okay, and this would be from Appendix C. I will search where I have 22, approximately 22 degrees is here. It's Mach number 184. 184, and mu2 for my geometrical drawing of flow structure is 33 degrees. Okay, 33 degrees. Pay attention to the following, that m or mu2 is always smaller than mu1. Should be always smaller. So flow accelerating reduces Mach angle, so it becomes closer and closer to body surface. Okay, so I have my Mach number 2, and I check mu2, and I check that it's decreasing, so my calculation considered correct, at least at this point. And now just temperature ratio. To define temperature ratio, I will go to Appendix A, which corresponds to my equation 840. I go to my equation, to Appendix A, just a moment, and I search in Appendix A temperature ratio. Since this is one comment I wanted to make with respect to this formula, is that inside appendix we do not have T2 divided by T02. We have T02 divided by T2. Okay, so I will maybe write on this part here. So I will put in reverse direction, right? I will put here as okay, T02 divided by T2, and here probably T01 by T1. So it would be equivalent to what is written on the screen, but I will use a reverse value from appendix. So my value corresponding to no, it's already reversed here, as we might see here. So temperature 2 and Mach 1 on the opposite part of ratio. So let me find here. We know that this temperature ratio should decrease, so it should be smaller than 1 because temperature drops. Let me find values that correspond to my Mach 1, Mach 2, Mach 1, 1.5, Mach 2, 184. Okay, just a moment. Okay, so parameter that correspond to Mach 1 I will put on numerator is 142, and in denominator corresponding to Mach 2 temperature ratio is 168. Okay, pay attention that this ratio should be smaller than 1. If you receive something that bigger than 1, probably you made a mistake on numerator and denominator position. Okay, now I will calculate just very fast. How much is it? It's 84.5 0.0845. And we have a drop of temperature as expected. Since we do not have a value of temperature as initial data, we can just talk about temperature ratio. And same thing we can do for pressure ratio. I will just make same consideration, and looking to appendix A, I will find pressure ratio and put in numerator and denominator. Here we can see also that formula is already inverted because our appendix A is having opposite or reversed relation, T0 by T and P0 by P. So for just a moment. For pressure ratio, it's 367. And for one, okay, it was 184, right? Yeah. 184, it's 6.21 or 611. Okay, so we can see that almost 2 times pressure drop. As we remember, pressure changes mostly among other thermodynamic properties. Then we have also some considerable change of density, and the smaller is change of temperature. So temperature ratio will be more closer to 1 than, for example, pressure ratio that would be closer to 0. Let me calculate this ratio. It's 0.6. 0.6 with a quite good precision. So we have 0.6 ratio of pressure after Prandtl-Meyer expansion. So this is how we calculate thermodynamic properties. Same we can do for density, but also if you need to know density after such transition, you can use simply equation of state, which is relation between pressure and density. Okay, and from here, density can be found. I can divide by just RT and remove from here. So density will be equal to pressure divided by RT for the gas. Do not forget that all units must be C, right? So pressure in Pascal, gas constant in joule per kilogram Kelvin, and temperature in Kelvin. Okay, so you will receive density also in C units in kilogram per meter cubic. Don't forget this, do not use temperature in Celsius. Do not use pressure in bar, because otherwise you will receive very, very wrong results. So all C units, everywhere C units. Please let me know if you have questions on calculation of Prandtl-Meyer flow. For my opinion, it's very simple, but if you found some difficulty, I would like to answer your questions today, just before you forgot. Question of calculation of Prandtl-Meyer flow is one of the questions I will give in oral test at the end of semester. So pay attention on such calculation. I also have videos about calculation of Prandtl-Meyer flow, several examples which I show. Since such flow is reversible, you can calculate not just from Mach 1 to Mach 2, but you can do calculation from Mach 2 to Mach 1, so calculate backwards. Sometimes it's also interesting, that tells us which conditions we must create initially to obtain one or other value of Mach number, or which condition we should be create to obtain some specific value of temperature and pressure. Just calculating backwards Prandtl-Meyer flow, you can answer those questions, because Prandtl-Meyer flow is reversible, can be calculated in both ways. Application of Prandtl-Meyer flow, main application is design of isentropic diffusers and design of isentropic nozzles, flows which are not losing entropy and do not lose energy, is probably the only way to design engines to fly in hypersonic conditions. I mean, fly not to descend, not to decelerate, not to return from space, but to fly like airplane or missile. There are several examples. Anderson shows just to motivate people some concepts of scramjet powered flight vehicles. Nowadays, there are several examples, and also in Brazil recently, last year was tested one of ramjet or scramjet engines supposed to work in hypersonic conditions. Would be very interesting to investigate what will happen in future with such project. The idea of such an engine is based on isentropic compression. We have a highly fast flow that is highly supersonic or hypersonic flow creates shock wave around the body. This shock wave is very near. Sorry, we'll turn off here. This shock wave is extremely close to the body, and it's usually oblique shock wave. After this type of shock wave, we always have supersonic flow. But to have an efficient combustion inside any type of engine, we must decelerate significantly our flow to subsonic or at least to low supersonic velocities. For this, we must create such a diffuser that would compress flow and decelerate with minimal possible losses in such a diffuser. And such a diffuser can be built based on Prandtl-Meyer, reversed Prandtl-Meyer flow. Reversed Prandtl-Meyer flow is shown here is the operation or compression is absolutely same as normal Prandtl-Meyer, but just flow is going in a reverse direction. It's not accelerating, it's decelerating. So flow velocity is high before, and after flow velocity is low, okay, much lower. Here you can see that since we have a shock interaction entering inside combustion chamber, that says that flow remains to be supersonic after this compression, but not so high velocity. After a series of shock waves inside this diffuser, this flow may have a relatively low velocity and to burn inside combustion chamber. You need to remember that when we are talking about Prandtl-Meyer flow or reversed Prandtl-Meyer flow, always we have flow rotation. Flow goes according to direction of flow. So here we must understand that flow is turning as well as in, sorry. It doesn't want to make curvature. Flow is rotating, okay, from horizontal direction to some inclined direction with respect to horizontal or initial axis of the body. And this is why this edge, lower edge of diffuser is not parallel to flow direction, which is entering diffuser. This is why even when we have low supersonic velocity entering inside diffuser, we start to have a series of reflected shock waves from walls. So such a reflected shock wave is caused by not symmetrical flow between diffuser wall and flow which enters inside. Okay, what else here? Something important we can say. As I already told you, this is the only type of diffuser which could operate on hypersonic flow, because as you remember, in hypersonic flow, we lose most part of energy. I mean, if we have just normal shock wave or simple oblique 1, 2, 3 oblique shock wave structure, we can lose most part of energy of flow, and such engine could not operate. Such a diffuser allows us to lose almost zero energy. Losses happen, of course, but these losses happen not because of shape or number of shock waves, theoretically infinite number of shock waves. We have here on each shock wave infinitesimally small losses, but these losses happen mostly because of friction of flow with the wall. Such friction happens in real flow. Boundary layer starts to happen, and heating of the wall also happens. So this transformation, irreversible transformation of kinetic energy to thermal energy we may observe on any real structure. So because of this, efficiency of real compression cycle is not 100%, but it's extremely high efficiency. Please let me know if you have some questions about reverse Prandtl-Meyer flow, if it was clear, if it was not clear something in this Prandtl-Meyer flow. Probably you could ask, at least I received sometimes questions about, okay, we have reverse Prandtl-Meyer flow, but what should be the shape? What should be the shape of the body to support Prandtl-Meyer flow? It's extremely important question. That shape of this body determines flow structure below this body. Okay, and to answer the question, what should be the shape? What should be the curvature? It's not linear. It's not simple curvature. Right? It's not just a line. It's sort of parabolic or hyperbolic. Cannot be expressed by simple parabolic function. Is a complex function that is obtained by integration of Prandtl-Meyer flow point by point. Such works we can find in the literature, and methodology to calculate such profile is quite well known. So if you someday will be interested to do research in area of isentropic diffuser and reverse Prandtl-Meyer flow, we have literature, or I have literature to recommend you to make such kind of study. There is a method. There are actually several methods. Some methods are simplified, and some other methods are more complex, but most of them based on solution of ordinary differential equations applied to two-dimensional flow to find a change of theta, change of inclination of the body with the change of Mach number along the flow. Quite interesting task, and this task can be solved by simple numerical method. Very interesting, I think, for studying. And there are several modern applications of such diffusers, so it's not just interesting, but also actual and important nowadays for scientific and technological research. At least I know that several institutions like ITA, EIA are working on this area. Okay, I hope they have a lot of success. Here in figure 932, we see a simplified sketch of such an engine. Such an engine has several parts. First, isentropic diffuser where flow is compressed from infinite to 0.4. Then there is a combustion chamber, a quite long combustion chamber, usually from 0.4 to 0.5. This size and aspect ratio, length to diameter, is high because the flow is fast. So when we have high velocity subsonic or supersonic combustion, we need to have long combustion chamber. Usually recommended values are close to 10 diameter. So length of a combustion chamber is 10 times bigger than diameter of combustion chamber, more or less. There are also some additional devices could be installed inside it to simplify combustion process to reduce these lengths. But these are technical questions you will see, I hope, in aeronautica and aerospace propulsion. Professor Domenico likes to explain a lot about such type of engine. Then after 0.5 until exit, we have a nozzle. In such case, this nozzle is not symmetric nozzle. Expansion happens due to increase of geometry on just the upper part. Here, lower part does not exist. Okay, so there is non-symmetric expansion, which generates significant value of thrust and allows movement of such flight vehicle. Here on table, we see, unfortunately, in imperial units, but we see typical values of operation. We can see that there is a Mach number corresponding such a project calculated different values of flight Mach numbers from 7 to 20 and corresponding altitudes. Altitude is different for different Mach number because engine works on a specific value of mass of air which enters inside the engine. So if we fly faster, we must fly also higher where density is smaller. So we receive similar or same amount of air inside combustion chamber. We cannot, unfortunately, fly at Mach 20 at low altitude because in such case, it will be so huge amount of air coming. So such an engine would never be capable to process such amount of air and would not be capable to work. So it's a typical characteristic of any scramjet or ramjet engine that with increase of Mach number, you need to increase altitude of flight to obtain same amount of air. Then we see Mach number, right, corresponding to this altitude at 0.4. We see that Mach number 4 is always remaining to be supersonic. Okay, but then it decelerates. After several or many reflections from walls, it decelerates to sonic or subsonic. In some cases, it does not decelerate until subsonic flow and remains supersonic, and such combustion is extremely difficult to organize technically. It's called supersonic combustion. Supersonic combustion is some advanced aspect that there is a lot of difficulties and many questions are still not solved technically. It's high energy combustion, which if someone feel like to work in future, it would be an interesting topic. Supersonic combustion is happening only in scramjet engines. In all other types of engines, I think supersonic combustion is not happening. Then there is area ratio, okay. Pressure ratio, with increase of Mach number, pressure ratio increases. We can see from approximately 50 times on Mach 7 entering, we have 50 times more inside combustion chamber, or at the exit of diffuser, entrance to combustion chamber, and we have more than 300 times increase of pressure at Mach 20. Since pressure increased so much, our combustion chamber must be resistant, mechanically resistant, and then when we look also temperature, it's not in centigrade, okay, but still very high temperature. It must be resistant to thermal loads and pressure loads as well. So must be used highly resistant, thermally resistant materials and strong materials for construction of combustion chamber, and such two limitations of temperature and pressure, creating huge difficulties in construction of such flight vehicles. We know that many advanced, or let's say highly developed countries have their own programs on hypersonic engines. The only way to fly with hypersonic velocity is to create such type of engine, And due to limitations of technology and materials, not all countries still have such engines. And this question of scramjet engine design already exists for at least 40 or 50 years, is discussed and developed in at least five decades. Still not solved definitively because of limitations of materials and technologies of fabrication. Please let me know if you have some questions. I'm just reminding you that you can ask questions. And just let's make 1 minute break. I will take a glass of water and then I will answer a question of Mauricio. Okay. I need probably to return previous question, previous slide. And here we can see increase of area between 0.4 and 0.5. The question is why the area in 0.5 is bigger. Question is extremely important. We must understand that area in such engine always must increase, because when we add fuel, we add extra energy, flow starts to expand. And such expansion can create such process called thermal block of flow. Flow expands in all directions, and if we hit too much, such flow can just stop because expansion is very big. So to compensate expansion due to chemical source and heating of flow, we must increase area of flow duct. So in such case, area 5 is bigger just to avoid thermal block of flow. You can observe such a problem in numerical simulations, quite typical. Especially, you also can see many of you when you simulate work 2, when you will try to simulate your diffuser. If you make too small exit section of flow, you can create also condition of thermal block when temperature increases, pressure increases in the exit section so much that it stops. There is always resistance of flow, so can stop due to many aspects, not just the heat addition, but also we need to think about growth of boundary layer that is rising, right? Each reflection of shock wave after 0.4 creates disturbance in boundary layer, which we will see very soon, and it also intensifies temperature and increases thickness of boundary layer. And all these processes, they cannot be just ignored. Need to do something to avoid this heat shock. We need to increase area just because of this. Unfortunately, there is no other way to keep area. We would like to keep area constant, but not possible due to energy addition and energy transformation. There is one one design. It's not new, it's quite old design of hypersonic vehicle, just to show you what could be a shape of a vehicle flying with supersonic velocity. There are several views. We see, first of all, is sharp edge, leading edge, starting point is sharp edge, and the trailing edge, final point of this body is also sharp edge. It's a long and thin body. It's very typical for such concept. Your body needs to be, or body of flying object has to be long and having sharp edges. In such a way, we can optimize or at least decrease influence of force oblique shock wave. Oblique shock wave always exists, right? Here on the top, oblique shock wave would be stronger, probably, right? On the lower side, oblique shock wave would be weaker, but always would exist. Even though if this edge or bottom wall is parallel to flow, shock wave will exist due to presence of boundary layer. Such a boundary layer is creating to us, let's say, some sort of artificial wall, and the compression of flow happens due to existence of boundary layer, because flow velocity inside boundary layer is smaller, so we need to have more space because some space is occupied by boundary layer. And due to this decrease of area, of flow area, with the rise of boundary layer thickness, we have very weak, but still we have shock wave. This design here, as you understand, is a concept, is not anything of final design and a balance. But I think it's a nice example of flying vehicle pretending to fly at hypersonic velocities. Probably you heard that recently several countries announced a successful test of hypersonic vehicles. I think it was China, right? It was Russia, maybe others, but unfortunately I didn't hear any of United States for such a vehicle. And we have some development in Brazil, so we can be proud of Brazilian science and technology that at least such projects, they are in development. They are considered as important. There are several projects which are not finished in in different stages of development. For example, this NASA X-43, it was designed a long time ago, I think, and was tested on some prototype. Wind tunnel were tested in some flight conditions, but as I know, there is no reliable information about complete design of this. Maybe it exists, right? But please let me know if you found some interesting information on this project or similar projects. I think would be interesting to update, even to make some small presentation here in a group of gas dynamics to understand what is happening with such developments all over the world. As I told you, it's the interest of many countries, including Brazil. So such a project always attracts attention. Anderson proposes to compare two different types of flow: compression wave and shock wave. Compression wave, which goes according to Prandtl-Meyer flow, is so-called isentropic compression corner, with the final angle of 15 degrees. And shock compression corner is shown on figure B, also having final angle of 15 degrees. So for both of these structures, we have same direction of flow of 15 degrees and the same initial condition of Mach 10 and pressure of 1 atmosphere. And it's proposed to see how different would be flow properties. So let's make some such a simple test, such a simple example. I think Anderson also shows how to solve it in example 9.10. But we can see here, just for you to understand process of calculation of such structures. We already saw how to calculate oblique shock wave, and today I showed you how to calculate Prandtl-Meyer flow. Here, as a reverse process, we can calculate compression wave. So we have theta 15 degrees. Let's make this calculation first. And Mach 1 10, this Mach 1 is biggest. So for us, I will find first Prandtl-Meyer function, okay, nu of M1 due to, according to formula previously shown of Prandtl-Meyer function, or I will use appendix C from Anderson. Okay, I see that Prandtl-Meyer function is equal, okay, let me check, 102. 102 degrees. Don't forget, it's given in degrees in appendix A, or sorry, appendix C. And I would like to then to calculate Prandtl-Meyer function on the exit M2. Second, my nu of M2. I expect that velocity decreases, so it means that my Prandtl-Meyer function also decreases. To calculate, I will use nu of M1 minus theta. And this would be how much? 87, right? 87 degrees. When I have Prandtl-Meyer function, I will calculate Mach number at the exit. I will look where is my 87 degrees in appendix C. I will take approximate closest value. It's Mach 6.3. Okay, I'm finished working with appendix C, and I can calculate pressure. I'm going to appendix A, and I will find my pressure for Mach 10 and for Mach 6.3 and find pressure ratio. Okay, so pressure 2, I will, okay, 2 is denoted here, so pressure 2 is right here, and Mach 2 also in this region here. Okay, just a moment, I will find Mach 10 and Mach 6.3. Value corresponding to Mach 10 stagnation pressure by pressure ratio will be 129. So pressure 2 by pressure 1 is 129 divided, then I will see 6.3 Mach. 6.3, it's 50, 51.6. 51.6. Then I will calculate this ratio and multiply by 1 atmosphere. Okay, it will be same. 129 divided by 51.6. 2.5. Yeah, looks like 2.5. I already write ATM because when I multiply by P1, 1 ATM, I will receive dimensional pressure. Oh, sorry. Probably in the such way will be not correct. I will just write right below that pressure 2 is pressure 2 by pressure 1 multiplied by pressure 1 is 2.5 atm. Please let me know if you found some error in my calculation, because sometimes it's possible. In such a way, I already found my pressure and Mach number after compression wave, and I will do same for shock compression corner. First of all, I will find beta. Beta according to theta beta M relation. Let's go back to diagram. Mach 10. Okay, where is our Mach 10? It's somewhere here where we have infinite and Mach 15, Mach 8, very close to Mach 8, between 8 and 15. And then I find my 15 degrees. It was 15, right? Yeah, it was 15. So somewhere right here. So I will assume 20 degrees of beta angle. When I have beta 20, mn1 is m1 multiplied by sine of 20. I will calculate. .4. Okay, more than 1. Our first checkpoint. It must be supersonic. Do not forget checkpoints when you write algorithm to calculate shock waves in work 1. It would be nice to make checkpoints, because if there is some error, you will identify it fast. So mn1, then I go to appendix B and search for 3.4 and find pressure ratio and mn2. Okay, already found. Pressure ratio. Oh, something is strange. 3.4. For me, it appears 13. Pressure ratio. Pressure 2 by pressure 1 is 13.3. Strange. Okay, let's see where could be this error. maybe in previous calculation. And Mach number after 0.45. Okay, Mn2 0.45 and 5 and M2 I will find by Mn2 dividing by sine of angle difference, 5 degrees. Okay, let me see if we get something realistic here. Sine of 5 degrees is extremely small value. $5.22. Okay, Mach number looks like corresponds to case A. We have 5.22. In case A, we had 6.3, so it's close. But pressure, unfortunately, does not correspond. I would like to go to this example in the book and see where is the source of my error. Okay, it looks like Prandtl-Meyer function is correct. Mach number is correct, but pressure ratio is not correct. Probably I took it from the wrong column. Probably yes, so I will need to check again my appendix from book. Yeah, I took a wrong value from appendix. Okay, let me see. Correct one. Inside appendix A. So these two parameters which I will need to verify inside this square. We must go to appendix A and see pressure corresponding to Mach 1 and Mach 2. Yeah, I took it not for correct value of Mach number. So I will make correction here. On the numerator for Mach 10, it will be 42,440. Very big value. Probably like this. And For the lower, for denominator, must be Mach 6.3. For 6.3, it's 2,135. Okay, now I will divide these two numbers and I will hope that result is closer to case B. Just a moment. Yeah, 1987. Okay. It was almost 19 in examples because I made some roundings, several roundings. In my case, it's closer to 20. In example 10, you can find something close to 18, 19. In my case, it's closer to 20. But anyhow, it's better than the first attempt to calculate. But always pay attention. Do not forget that we must have some checks, right? For example, in this calculation which I perform, I compare case A and case B. They could not be so much different. So much different. Okay, at least 19. And if results are too much, okay, 5 times, 10 times, probably something is wrong, right? So here I compare values, understand that hypersonic flow is highly energetic. So for example, pressure ratio cannot be too small. But since it's a compression wave, I was thinking, okay, maybe it's so good, it's so efficient compression that pressure didn't rise so much. This is why, but already had this attention because pressure ratio of 2.5 corresponds to just supersonic, simple supersonic flow, does not correspond to hypersonic flow. And this also has to be confirmed. Every time you receive some value, think how can check. If possible, to make double check, if possible, to compare with some other solution. Critical thinking is always important in aerodynamics and also in other engineering science. In any engineering science, critical thinking is important. Must be questionable parameter. You must question yourself, did I do it correctly, or I have a way to check if it was okay, or okay. If not possible to check, we can consider wrong calculation. Because always must be a reference. Our reference in numerical simulation, for example, is analytical solution. Our reference also can be experimental testing. Need to have several sources of data to compare. So this another example which I show you today, I made a mistake, but okay, I question myself why it's so different results. So need to check. This is how everyone should think, that if you are not sure that you obtain correct result, find a way to find a mistake. Okay, I hope it was interesting or useful at least. Anderson also proposes shock expansion theory to calculate supersonic airfoils. Just very briefly passing how it's calculated. Structure of airfoil or plane shows on just a flat plate that is inclined to some angle of attack alpha. We can see on this flow picture two flow processes happening in parallel. On the upper part of this airfoil, we have expansion fan Okay, flow expands. And on the lower side of this airfoil, we have a shockwave, oblique shockwave. Flow goes through oblique shockwave. Of course, when it goes through expansion fan, pressure decreases, so it's a relatively small pressure on the upper side of this plate. And when it passes through oblique shockwave, pressure increases. So there is a considerable pressure difference between upper and lower side, and there is considerable lift and also drag. There is lift and drag, both parts, right? Lift is a projection of force on vertical axis, as you may see here, and on vertical axis, no, on horizontal axis, but it goes vertically. Right, and drag is projection on a vertical axis and goes horizontally, drag. Here we do not consider viscous forces, just pressure forces. Just pressure forces, very typical situation. Here, C cosine alpha, C sine alpha is giving to us projection on horizontal and vertical planes. Okay, and inside brackets we have pressure difference between upper and lower side. So pressure difference multiplied by area, projection area, we receive force. Okay. Another example is this one, where flow passes first through oblique shock waves, where pressure increases, P2 is higher than P infinite, and then it passes through expansion waves. In region 3, pressure decreases with respect to P2, but it still remains high and contributes to creation of drag. Here we have zero lift because flow direction is same as symmetry line, so there is no lift force, but there is a drag force due to action of pressure. And this can be calculated analytically because we know how to calculate oblique shockwave, and we know how to calculate now Prandtl-Meyer flow and pressure transition. So after, do not forget very important thing that shockwave, Prandtl-Meyer flow, and shockwave again. So we have, let's say, repeating flow structures here. If you have shockwave in other part, you will also have expansion wave. If you have expansion wave, another part, you have also shockwave. They always complementing each other. It's not possible to have just shockwaves. You will have both shockwaves and expansion waves. Same you can see here on this upper example. Shockwaves on one side, expansions on the other side. First you have a shockwave, then you have, first expansion wave, then you have shockwave. On the lower part, opposite. First shockwave, then you have expansion wave. They both complement each other. Another example Anderson proposes to solve is influence of or importance of design of a tail. Probably we can leave it for our next lecture. Today is not enough time to describe fully such calculation because I would like to show you some part of this calculation. And here we will see why it's important to use a well-designed tail instead of just using flat plate as a tail. You will see that design makes a big difference in efficiency of flow. At this moment, I would like to finish for today. Please let me know if you have questions. And I'm expecting, let's say, 1 minute. And after answering your questions, or if there will be no questions, we can finish for today and we meet on Thursday. Please do not forget that you can also ask questions about work 1 when they appear. Maybe next time or next week. Many questions I already answered about work 1, including some aspects of calculation, how to do format, how to extract data. You can find them in all previous videos. But if you still have questions, I would be happy to explain. Okay, I think there are no questions. So thank you for participation today, and we meet on Thursday, probably. See you next time.
Thanks, Professor.